steps. One is, first of all, you don't know, even though you might be asked to determine the mass moment of inertia, first of all, you have to determine the center of mass. And that center of mass itself might not be known because it's a complex shape. So you have to go to find that center of mass first based on the centers of masses of each of the parts. Once you know all the CIs from the tables and C from your calculations, now you can go from ICI to IC. Okay, so to do that, you will simply use the parallel axis theorem. The mass of each part multiplied by the distance between the centers of masses of those two parts, of course perpendicular to the z-axis. So that's the distance that we are talking about. And once we do that, we can eventually get to the, that is for just the ith part. Now to get for the whole rigid body, you have to sum over all those parts that it is made out of. When you sum that, this is the expression that you get, that it is for each part about its center of mass, then using parallel axis theorem to get about the overall center of mass, and then eventually summing over all the parts to get the total rigid body's mass moment of inertia about the z-axis passing through the overall center of mass. Okay, now the concept that you brought up early on, radii of gyration. Okay, in singular, of course, it's called radius of gyration, but there are more than one, so we call it radii of gyration. That is the plural. Now the mass distribution measures are defined through your mass moments of inertia, IZZ, which is about the z-axis, through either a center of mass or through the arbitrary point P, and both of these can be defined in terms of a new quantity we want to introduce through this, which is K. Okay, and K again, just like angular momentum, depends on the point about which the rotation is taking place or about which you're interested, which could be either the center of mass or any arbitrary point. So depending on that, it's either called Kc or K subscript P. Okay, so this is just a definition for Kc or Kp. These equations is a new term that we are introducing called the radius of gyration. We are saying that if we have already determined the mass moments of inertia, we can introduce a quantity called Kp or Kc, which is just the square root of the mass moment of inertia divided by the mass. Because mass plays a very critical role in translation, I plays a very critical role in rotation, right? So M and I, the ratio between them is a very interesting feature as well, because it's kind of a measure of how much each of them is, one is dominating over the other, the rotational and the translational. So that is what your Kc squared or Kp squared measures, and therefore this becomes very critical. And in many cases you will see that in those standard tables, not only you will be given center of mass and I, but you will also be given Kp, even though given I, you can very easily determine that from the total mass of the bodies, but nonetheless those are also typically given. And if we just substitute this in the parallel axis theorem, remember that those two i's were related by just a d squared times the mass. The mass is the common term in all three of them. The mass cancels out, and just you have this, that the radius of gyration about any arbitrary point P is given by the radius of gyration about C, both of course squared, plus the square of the distance between C and P perpendicular to the Z direction. So that's essentially your formula. So once again, you see, just like in the previous case, we said that IC was the smallest of all the I's. Similarly, Kc is the smallest of all the K's. In other words, the lowest radius of gyration will be about the center of mass. Okay. Okay, Euler's second law of motion, now we take it up for the 2D rigid body about a fixed axis. Okay, so far we've allowed for the axis to move around, but now we are fixing that particular axis. In other words, it could be inertially fixed, or it could be common between the rigid body and the inertial frame, in which case it becomes an axis of rotation, right? So when you have a 2D rigid body which is rotating about a fixed axis, even if that axis is not passing through the center of mass, you still have this particular simplification, and you can just see this by making the substitution for the fixed axis, because if the axis is fixed, the velocity of all points on that axis are 0. So just by substituting the velocity equal to 0, you will see that this becomes a straightforward thing. Because remember that the the sum of the moments which are acting on the body about p, which becomes essentially a scalar equation, because there's no mp about x direction or y direction. Along x and y, only translations are taking place because it's 2D motion. Okay, in 2D motion, only translation along x and y, and the only rotation is about the z axis, and therefore it's a scalar equation. And we already showed that that particular moment is equal to the mass moment of inertia about the same axis z, about passing through p, because the moment is also calculated about p. That's why this is also p times the angular acceleration alpha, right? Which is of course along the z direction, or k hat if it's a vector, right? So that alpha can be written as either as omega dot or as theta double dot. Once again, straightforward things that you can see. Okay, I don't know, maybe I'll do a few slides so that we can definitely avoid next Thursday. Okay, so rolling and slipping, this is something that we have seen from the kinematic point of view already. Okay, so now we want to see it from the kinetics point of view. In other words, we have to bring the sources for that. Okay, and we have already seen that in order for this to happen, there has to be a force, which is the cause of the motion. Okay, that cause of the motion, if it is passing through the center of that body which is rolling, then obviously it cannot create a torque, because the motion is happening about that center. So it has to be away from that center. The line of action of the force has to be away from that center. It has to be at a certain distance. And one such force, of course, is the friction, because the friction is going to be tangential to the circular body, be it sphere or cylinder, and therefore it is having a moment arm, which is the radius of the ball or the cylinder that you have. Okay, so it could have incline. On the other hand, you could also use pulleys. You could use ropes, strings, or cords in order to do the pull. Essentially, you are creating that tangential force, and which is therefore having a moment arm, a non-zero moment arm, and therefore can create a torque and therefore a rotational motion. Without that, unless the rotational motion is already in place, it cannot be introduced unless you have a torque. Just like a translational motion cannot be happen unless there's a force. Similarly, you need a torque, and for the torque to be there, you should have not only a force but also a non-zero moment arm, which is what we are talking about here. Okay, so an incline that you see something over here, because of gravity, you see that is going to roll down. But if there is no friction, it would just slip. It would not be rolling down, right? So similarly, you can have a cord around that, and you could pull the cord. And then remember, the one of the examples that you were talking about today was on a track, but the same thing you can think of as two different radius that thing had. If you tied a cord around that and you pulled the cord, it's like a top that you're trying to get to spin. So something like that, you see that will start spinning over there. Okay, so various other ways in which this can be introduced. Now coming to the 2D rigid body equations of motion for this particular case where rolling is involved. So dynamic equilibrium equations employing resultant force and moment acting at the center of mass, right? Now these are the equations that we have. This is very similar to what you used to do in statics also. You used to get to the forces and the moments. You to break it up into components or measure numbers along the XYZ direction and set each one of them equal to 0 there in statics. But in dynamics, you can't set them to 0. You have to set them to the mass times the acceleration if it's translational, or the moment of inertia times the angular acceleration if it is rotation. Okay, so you see the parallel between that. And this is something that when it was taken to the left hand side, we called it as a D'Alembert's force. Similarly, this can be thought of as a D'Alembert's torque. If you take it to the right hand side with a negative sign, then you still are dealing with quasi-static kind of equations, all of the right hand sides being equal to 0. But Right now we will not do that, and we will see that treat it as a right Royal dynamic problem with the right hand sides being non-zero, involving accelerations, both translational acceleration as well as rotational acceleration. The only simplicity that we have brought in is instead of 3D we are looking at 2D, so that rotations can pretty much be dealt with as scalar quantities, and here because we are breaking the x and y also separate equations, even the forces can be treated, or translations can be treated as scalar equations, the way we have written this down. Okay, so now what is the source of each one of these? You see that essentially it comes from the Newton's second law, which force is equal to mass times acceleration. You can identify these xc double dot, yc double dot as translational accelerations. You can identify theta double dot as a rotational acceleration, what we called as angular acceleration alpha. And all these are of course about the z direction, those are about x and y respectively. Okay, so this is the path, remember, that we took in the morning's class. We started with Newton's second law. We extended it from a single particle to a set of particles. Then we talked about the set of particles becoming a rigid body, and therefore we got on to the Euler's first law for translation, Euler's second law for rotation. Okay, in general, of course, 3 of those and 3 of these, but that's for 3D motion. Here we are dealing with only 2D motion, and therefore there are only 2 translations and 1 rotation. So the 2D vector equation for translation and 1D scalar equation for rotation is what we have in this particular slide for 2D rigid bodies. Now let's talk about the forces on rolling or slipping, hollow or let's say solid, cylinder or sphere. Okay, so we have various options that are available. Either the body can roll or it can slip. Okay, of course we talked about skidding as well the other day in the online class. As far as the body itself is concerned, it could either be a cylinder, in which case the contact is a line contact, but since we are looking at only one particular cross section, that again becomes a point. If it's a sphere, it's already a point. Okay, now both cases, whether it's cylinder or sphere, it can be either a solid cylinder or solid sphere, or it can be a hollow cylinder or a hollow sphere. Okay, so we are trying to learn about all these things simultaneously, because we have introduced this concept of the moment of inertia I about the z-axis, which is about the axis of that cylinder or axis of any axis of that sphere. And because the cylinder has just one axis, whereas the sphere has infinite number of axes, as you know, passing through the center. So which of course we are interested in one particular axis about which the rotation is taking place, even in the case of the sphere. Okay, so since we have introduced this concept of I, all of those I's, whether it is hollow or solid, cylinder or sphere, are all going to be proportional to mr squared. What is mr squared? M is the total mass of this sphere or cylinder, hollow or solid, and then the r is nothing but the radius, the overall radius of the cylinder or the sphere. So in all 4 cases, this combination of hollow, solid, cylinder, sphere, all 4 cases, it's going to be a multiple of mr squared. But what is going to be multiplying mr squared is what changes in each one of those cases. And typically for a lot of applications, especially in aerospace, when we are talking of hollow, we are not talking of a thick-walled hollow case, we are talking of thin-walled hollow. Okay, so that we can utilize material effectively and bring down the weight of the aircraft. For example, the skin of the fuselage or the skin of the wing, etc., are fairly thin compared to the chord or the overall cross section of the fuselage, etc. Right? So when you have such thin geometries, then you will see that out of these 4 combinations that you have, hollow, solid, cylinder and sphere, there are certain combinations which are going to be much more effective than the other. Out of those 4 combinations, which do you think is the best in terms of increasing your I to the maximum level? Between hollow and solid, yes, hollow is correct. Between then now you have 2 more options left: hollow cylinder, hollow sphere. So what we are interested in, remember, is 2D motion. Okay, so it's the moment of inertia about the z-axis, which is the axis of rotation.
Would it be the cylinder then?
Why?
Because more of the
Very good. Yeah. So in the sphere, as you go away from the center, you're seeing that even on the axis of rotation, some of the material is coming closer to the axis, and therefore it's becoming useless, okay, or very less effective. Whereas in the cylinder, thin-walled cylinder, all of the material is outside. So pretty much if you have a reasonably thin cylinder, for all practical engineering purposes, you get 100% of mr squared that you can retract, okay. What is the worst case scenario? Solid what?
Solid sphere.
Yeah, solid sphere. So you, what do you think would be the percentage that you get of mr squared over there? So in this case, you get full 100% when you have your hollow cylinder. Okay, hollow cylinder, your IZZ about the C, center of mass, is just mr squared. Okay, whereas when you go to the other cases, it keeps on reducing until it becomes the worst case, as you said, the solid sphere. So it becomes just 50% of that. Okay, so it's just 50%. So 1/2 of mr squared is what you will get for a solid sphere. The others are in between. Sorry, it will be about 40%. Okay, so the others will be in between, like 50%, 67%, which is 2/3, etc. Okay, so this is these are things that at least in a relative qualitative sense, it's important for us to remember, because as designers, especially when you're looking at aircraft, etc., for dynamics, many of these come in quite handy in terms of intuitively thinking of certain shapes over certain other shapes, even before we get onto actual calculations for that, which eventually are required. But you can preclude a lot of choices, because design is all about making choices, and if you have too many choices, always a confusion. So there are certain choices that you can obviously leave out, and then you can focus on a few more, and then you can have more, let's say, reliable, high fidelity kind of models for that, which require a lot of computational effort. So you don't need to run it on all the cases. You need to run it only on cases which you think are kind of candidates which can probably go further down. Okay, so that's as far as that is concerned. So now in terms of the forces acting on this, one is already shown over here, which is the weight, self weight of the cylinder itself, which is the mass of the cylinder or sphere, solid or hollow, times the acceleration due to gravity. So that's the, because if gravity is not there, G will be 0, and therefore that force will not be there. Okay, now it's the resultant acts at the center of mass, which is for a uniformly distributed case of both cylinder and sphere, you will have it at the center of that, which is geometric center of that. Okay, but in reality, what is the situation? It's actually each one of those DMs, small DMs that we've been talking about, the infinitesimal masses, all of them actually are acting, and each one of them is acting downward towards the center of the Earth, and if it's the Earth's gravitational field that we're talking about, and it's the sum of all of that which we are drawing at the center of mass and calling it as mg, right? So distributed gravity load is statically equivalent to a single force at the center of mass. This static equivalence is something that you would have studied even in statics. Essentially, you're replacing a set of forces by a single force or another set of forces, which is going to cause the same effect eventually, and which is what we have over here. Okay. So now let's look at this. In addition to the force that we talked about on the previous slide, which is the gravity, we have the normal force, which is essentially again coming from Newton's third law. Every action has equal and opposite reaction. So the ball or the cylinder is exerting some force because of its weight onto the plane or plank on which it is there, which could be either horizontal or inclined, like what you see over here. In either case, there is a normal reaction that is coming, and which will be perpendicular to the plank and also perpendicular to the surface of the cylinder or sphere at that point, and that we will call as N, the normal force. Okay, so this is the normal reaction that we have. So the first force we already talked about, weight. Second force we are talking about is the normal reaction. Okay, it acts at the line or the point of contact. Okay, so if it's a cylinder, it's a line of contact. If it's a sphere, it's a point of contact. Acts perpendicular to the contact plane. That's quite obvious. That's why, in fact, we are calling it as a normal reaction. Okay, so it's not that the interaction between these is always normal. There is, in fact, in an arbitrary direction, because we can break that up into a normal force and a frictional force. The frictional force is tangential and the normal force, okay? So right now we are only considering the normal force. So in general, you have an arbitrary direction force because that's the resultant of the normal and the frictional force, okay? So there's no assumption or approximation involved here, which is what I wanted to bring to your attention, okay? So that's perpendicular to the contact plane by its very name. And it's calculated using static equilibrium because there's no motion which is perpendicular, unless of course you're bouncing the ball on top of this. Here we're only considering the problem of rolling or slipping, or essentially the contact remains a contact point, okay? It's not getting out of contact, these two bodies, okay? So as long as they remain in contact, you're going to have a normal force, and therefore you can see that since there's no acceleration with respect to them, in other words, the velocity in the normal direction is not there for either of these bodies. Therefore, you see that statics applies. You don't need dynamics to calculate that. Static equilibrium equations, so no motion or dynamics in that particular direction. Okay, so we finished weight, we finished normal force. We come to the third one, which is friction, right? Friction could be directly between the body and that, or it could be through the rope or string or cord that we talked about in the very first slide on this. So it could be any one of them. Simple case, we'll take between the rolling body and the plank, okay? So now the question is which particular direction will it act? Whether it will act in this direction or this direction. How do you determine that? The friction force.
Which way the ball is rolling.
Exactly, right? Yeah. And there are two types of friction. You remember that? What are they called?
Static and dynamic.
Exactly, right? So when you're just about to start it, then it will be typically a little higher value, and then it will become a smaller value, and those coefficients of friction I'm talking about will have to be appropriately taken depending upon which phase of the motion you are actually involved with, okay, or calculating for. So it acts at the point of contact. That's where it acts, the force, the frictional force. And in this case, where it is rolling down a plank, it's very clear that it's in the upward direction that the frictional force is, okay? But of course, remember that we are talking of two forces over here. Newton's third law, the plank is exerting a force on the rolling body, and the rolling body is exerting a force on the plank. That's the case with N as well, okay? Whether it is N or F, when we are talking about the direction, we also have to mention of which body on which body, because the other one will be exactly opposite of that, okay? So just be aware of that. So then the frictional force acts along the plane of contact, opposite to slip, and then you have an opposite in direction to the relative velocity. So as you already mentioned, if there were no friction, okay? Now proportional to the normal reaction, that's how you have. So that coefficient of friction multiplies that normal force to give you the total force, the frictional force that is there tangential to the point, to the plank and to the body as well at the point of contact, okay? Coming to friction on rolling versus slipping rigid body. Again, some of these aspects we covered without giving equations when we discussed this in a virtual class, but now that we have have already moved from kinematics to kinetics, we have brought in the forces, and therefore we are in a better position to mathematically model it, okay? The maximum friction of course depends on the normal reaction, because more the normal reaction, more the frictional force, okay? And of course it depends on the coefficient of friction. So more the coefficient of friction, the larger it is, okay, between the two surfaces. So your F max, the maximum frictional force that you can have, is mu times N that you have, right? Now during rolling, with or without slipping, the magnitude of your F will be less than or equal to your mu times N, okay? So when will it be equal and when will it be less than? Come again?
If it's accelerating down the hill.
Okay.
If you are rolling, it will be maximum. Because you are slipping, it is friction.
Correct, yeah. So that's what distinguishes between whether it is pure rolling or rolling with slipping. So essentially when it is maximum, when it is equal to, it will only roll, it will not slip. Okay. So during slipping without rolling, then you have it equal to. Okay. So this is the distinction that remember we were talking about in a very qualitative sense. It might have looked hazy when we were talking about kinematics, because at that time we were not talking about the source of this motion, namely the forces, and therefore it looked a little bit hazy. Okay. So we either know the friction force, that is if it's slipping, or have the kinematic constraint if it is rolling. Okay. So that's how you're talking about these two situations, because in one case it's an inequality, the other case it is an equality. Okay. Now I don't know, maybe because there's a lot more that I need to do with rolling, so maybe I will come back to this in tomorrow's virtual class, where we will start with this and then combine both. Okay. So far in the few slides on rolling and slipping, we have looked at essentially the kinetics, because we looked at three forces: normal force, weight, and the frictional force, and we saw the correlation between them. And now we want to revisit what we talked about kinematics there, and then eventually combine both, so we'll be able to solve this problem in a much more effective manner. Thank you.